Okay, so in chapter 21 of the text, we discuss epidemics, and this chapter looks at things more from a social standpoint and analyzing epidemics from the social network standpoint. We can also look at this from a mathematical perspective in terms of differential equations, and we actually do that in CS408. So I'm going to keep that material for 408 kind of separate from what we're doing in CS485. So, basically, it's a somewhat timely topic for us, given the impact that COVID-19 has had on our society. Certainly, we probably wouldn't be doing things over Zoom and as much as we are now if we did not have the COVID-19 pandemic. And, it's still, even 4 to 5 years on, it's still having quite a bit of impact on our lives. But this has always been a topic where we mix biological issues with the social ones, and that makes it somewhat controversial and difficult. The authors in this textbook talk about Jared Diamond's book "Guns, Germs, and Steel," which looks at the impact that disease had on native populations during the colonization period. And it's definitely an interesting read. I believe there's also a National Geographic series that was done on this very thing. So definitely worth a look at that book. So the patterns by which epidemics and disease spread through groups of people is somewhat determined by the properties of the pathogen carrying it. How contagious is this? Now, how long does a person remain infectious after they contract the particular disease? And what is the severity? The severity of the disease is too much, then people won't be able to spread it, oddly enough, or as effectively because they're not out and about in the general population. So there's sometimes you hit the sweet spot, which we kind of did with COVID-19, where it was very contagious, kind of a lengthy infection period, and it was severe, but in most cases not severe enough to prevent the person from going out in public. In fact, there was an asymptomatic stage where they were contagious but weren't displaying symptoms. So, that kind of made COVID-19 a bit of a perfect storm. But in addition to the properties of the disease itself, the patterns are also influenced by the network structures within the populations that it affects. So we can study certain things such as transportation network or do contact tracing. And we can even use these social patterns for understanding the spreads of things that are not human pathogens or pathogens that affect humans, such as computer viruses. Although I suppose those do impact humans. So different diseases kind of give us different networks. For imagine a highly contagious disease that involves airborne transmissions based on coughs and sneezes. That might be something like COVID-19. The contact network in this case is going to be a huge number of links. Basically, any people sat together on a bus or an airplane came in contact with one another in a store, classroom, any public space that was an enclosed public space. So, you get a very large social network with a lot of links. On the other hand, consider something like a sexually transmitted disease or something that requires close contact. The contact network is going to be much sparser with very few links between people. In fact, I think SARS-CoV-1, you basically had to be in the same room with someone for a long length of time when that one came out in about 2003, 2004. So, depending upon how the disease is spread, the network will actually be different. So there's also some connections between epidemic disease and the diffusion of ideas through social networks. Like you say a video went viral. So there are similar structural mechanisms to the extent that the spread of ideas is often referred to as the social contagion. But they are different because we choose to adopt these ideas or choose to consume and enjoy these videos or experiences online. But we don't necessarily choose a disease. In fact, I think most of us would probably not choose the disease. So infection in these types of networks is often modeled as random. So let's take a look at the models, and we're going to take a look at two of them in one variant. The first model is the simplest, and that's the branching model. And this is one that uses waves. So the first wave is when a person carrying a new disease enters the population. We call them patient zero. They transmit it to each person they meet independently with a probability of P. Suppose this person meets K people while he's contagious. We'll call these K people from the first wave of the epidemic. Some of them will get it, some of them will not. Again, there's that probability P. Perhaps you have some immunity, or you weren't in the room long enough with the person to receive the transmission of the disease. The second wave, each person in the first wave goes out into the population and meets K different people. So the second wave will have K squared people. Each infected person in the first wave will pass the disease independently to each of the second wave people they meet independently, and again, it has that probability P. Subsequent waves, third, fourth, fifth, etc., will work the same way, and we get a tree-like model for our contact tracing network. And in fact, people will often look at, like earliest common ancestor, when we were looking at our family trees, as a way to find that patient zero. Even though they may not be the first person who had the disease, they'll trace that back to the patient zero. The extent of infectiousness is based upon the contagion probability, that P. If the disease is a branching process, then and it fails to infect anyone, then the disease dies out. And but there can also be the case where it continues to transmit through the network until either everybody's exposed or there's a re-exposure possibility. If R is less than R0, the reproductive number is less than 1, the disease tends to die out. If it's greater than 1, then it will persist throughout the entire model. R0 is equal to 1 is called the knife edge case, and in that case, it makes sense for health authorities to try to adopt mitigations to get that number below 1. The second model, and the more complicated of the two models, is the SIR model. And this can be applied to any network structure. It's not just the tree. Basically, we preserve the basic ingredients of the branching process model at the level of the individual nodes, but make the contact structure much more general. And this one has a 3-stage life cycle. They're susceptible, where basically I haven't caught the disease, but I'm susceptible to infections from my neighbors, my coworkers, my friends, colleagues, etc. The next is the infectious stage, where I've caught this particular disease or contagion and have some probability of infecting my susceptible neighbors. And then the last one is called removed in our textbook, and it's called recovered in others, but it's the R. And so this is after a particular node has experienced full infectious period. It gets removed from consideration, so it no longer poses a threat of future infection. There are some diseases where you can catch it once and then you get the immunity to it. So no one gets added to the susceptible group here because we're ignoring births, immigration into a particular country or particular social network, and we're ignoring the possibility of reinfection in the base SIR model. And so we also have a fixed fraction K. The infected group, they'll recover during a given day. So how would this work in a social network? So suppose we have this following simple social network. We start out with Y and Z, both being infected and contagious, and the rest of them are susceptible. Y is in contact with T, Z is in contact with X and V. And so on the next pass through, we see that X and V get infected. Now, V is in contact with W, and X is in contact with R. Y is no longer infectious, so T isn't at risk at all at this point. So imagine that R becomes infected, but W gets lucky and doesn't become infected the same way that T did in the last step. Same with S, gets lucky and in the final step where R is the only one that's infectious, S doesn't get the disease and the disease dies out. So, we can see here that 5 people caught the disease and 4 people did not actually catch this disease, but the disease died out because there's no one who's actually infectious at this point to spread it. We can extend this SIR model to make it more general and to deal with different cases. And we can modify it to have different probabilities between different types of connections. My probability of contracting, COVID-19 is quite different if I'm at an outdoor park and hiking along trails and walk past somebody who has it versus being a close personal contact that I'm working with in a physical classroom. We can also choose to model the infectious periods as random in length. Some people are infectious for longer periods. Some people are infectious for shorter periods. And so we can have a probability of recovering at each step while we're infected. And we can also break that infected stage into several different stages, beginning, middle, and end stages. And those can have different properties for infection, morbidity, etc. The final variation on the SIR model is the SIS, and this is where reinfection can occur. And so this is a situation like COVID-19, where you can actually get this thing multiple times. So an SIR epidemic on a finite graph, it burns through the bounded supply of nodes since they can never be reinfected, or the ones with immunity can't get it. The SIS epidemic can run for an extremely long time as it cycles through the nodes potentially multiple times. And I think we all know folks who have caught COVID-19 a couple of different times. And so there's a possibility of so we can represent that type of situation. And what's interesting is we can do some of the basic variants of the SIS model as special cases of the SIR model. So SIS is different because there is no recovery. And that's it. I'll save the mathematics and the fun differential equations for CS485. Thank you so much.